Usually we use this notation A, then we transpose. Okay, if the size is n by n, after transpose it becomes n by n. That's it. Okay, just interchange the number of rows and the number of columns. Okay, the code transpose. Usually we use we prefer use the okay, or A prime. That'll be fine. Okay, so okay, and so this example just show you what is the matrix A and what is the corresponding transpose. So that's it. Okay. So if both are the same, then we say the matrix A is symmetric. Okay, it's symmetric. 就说你行列换的话，它都没有动，那我们就说它是 symmetric. Okay. Now, just some terminology you need to remember. Okay. To matrix you can add. Okay, to matrix or subtract. Okay. So that's it. Of course. To do that, both must have of the same size, right? They both must of the same size. So you can do the addition or subtraction. Okay, so you give the example here. Okay, you just do the addition, so the result C will be just the corresponding element. You just add, okay, do some arithmetic addition. That's it. It's quite simple. Okay, you can remember. Now we talk about the multiplication. Okay. We just multiply by a constant scale. It can be instead we can put the constant k for each element in the matrix. Okay, that's it. So we just change the scale. Okay, we can change the scale with some constant k. Okay. Multiplication, a little bit complicated, but it's very important when you read your class note. If you know how to do the multiplication, then you will know how to interpret, okay, what is the equation in the in your class note. Okay. Anyway, A times B. Okay. Here's some requirement. You can do the multiplication. Okay, the first the condition must, if A can times B, it means both they must be conformable. Okay, it must be inconformable. What does it mean by conformable? If the size of A is m by n, then the row of B must be n by anything else. Okay， 也就是说 A 的列它的 column 一定要跟 column 数一定要跟 B 的 row 的数目一模一样，这个叫做 conformable， 不然的话你没有办法相乘。所以当你在读老师那个课堂讲义的时候，因为有时候会写你就可以看得出来他到底在做什么，因为有时候你会乱掉。Okay, the representation, I mean, A or A transpose could be a little different. They might have a different meaning. Okay, they might have a different meaning. Okay, especially, for example, when you represent a time series data. Okay, you have time series data 1, and you have a time series data 2, and you might have a time series data 3. Okay, the length could be, for example, could be 100. Then the dimension is what? 3 by 100. Or you can represent it by, you know what I'm saying? The meaning could be totally different, especially for ICA, independent component analysis. Okay. 所以呢，你不管是用漏放或 column 放，它指的意义可能不太一样，这个要小心。Especially when you use the software tool, the input could be. I mean, you cannot get the result you expected. it may not be, it's nothing wrong with the algorithm or with the programming code, but something wrong with your input. Okay, you must be very careful how to input by row and by column because the meaning could be different. Okay, let me just quickly give you the example. If I say independent, x1 and x2 are independent, it means what? Given at some time t, I observe the outcome of x1 cannot help me to estimate the output at the same time for x2 and x3. You know what I'm saying? 比如说我看到 x1 在某一个时间点 t， 我讲说它们三个都是独立的，是我没有办法看到在同一个时间点 s2 会变成什么 s3 变成什么。But if I talk about the independence here, this is x1. And I say independence, it means what? I observe some x2 at time t. It won't help me to estimate at another time k. You know what I'm saying? This is the independence across the sample, but the independence is across different time steps. You know what I'm saying? Okay, yeah, that could be. So it's very important how you represent your matrix through the tool you use for machine learning. It's very important because the interpretation could be totally different. Okay, I will talk about more. Okay, later on. Okay, but anyway, you have to make sure. Okay, if you have a matrix n by n, b must be n by something. The result. The size will be m by p. Okay, so that's it. Just remember this. So when you read my class note, you will understand what does it mean and how to operate your input data. Okay, so just try to remember. I know every one of you can do the multiplication of two matrices, but it's very important. Okay. Just to refresh your memory, and when you go through the algorithm for machine learning, okay? Okay, as I mentioned here, this cannot be done, okay? If n is not equal to p, now there's no way you can do the multiplication. But when you ask ChatGPT, it might give you the answer like this. Okay, it could happen. So don't trust ChatGPT all the time. Okay. Okay, so here's the example for multiplication. Okay, so the row times the corresponding column, element in the column. So that's it. Okay, so just follow. Okay, I don't need, here's give you some numerical, okay, example, how to do the multiplication of two matrices. Okay. Here's a times b. This is a special case. Okay, for this case, you can interchange a and b, but it's not always the same. Okay, it may not be. Okay, unless the number of columns of the first matrix is equal to the number of rows of the second matrix. Okay, but this is just a special case. It may not be true. Okay, it means a times b usually won't equal to b times a, or even it's not possible. Okay, it's not conformable. Okay, and here we b times c, then we times a, and we can write it as a times b first. Okay, and then the result we times c, and the transpose of a times b equal to, now it is very important. Sometimes you will read the equation here. Okay, a times the transpose of a times b can be written down as B transpose times A transpose 啊 ，A 跟 B 相乘以后取它的 transpose 行列互换，会等于先做 B 的 transpose 再乘上 A 的 transpose。OK， that's something you need to keep in mind. OK， it's a very popular matrix A transpose times A. OK， this is the result. OK， you get this is the total number, right? This is the total number, this summation of, okay, you can see something here, okay. They usually, you can see E transpose times E. This is another very important computation. Usually you will see, it means, usually you imply you are doing eigenvalue, eigenvector transformation, okay. 这是那个矩阵里面那个中文叫什么不知道，知道老师，反正我会强调比较不知道，以后我会谈这个很重要。Usually this eigenvector will tell you the projection direction。我刚才讲过，我们谈这一学谈很多都是在做投影 ，and this eigenvector will tell you the projection direction。OK。OK， diagram， OK， 对角啊 ，OK。The diagram, this is the diagram matrix. Only the diagram will show non-zero elements, okay? And all other up diagonal have the value of 0, okay? This so-called diagram matrix, 对角, okay? And this identity matrix, okay? All the diagonal element has the value of 1. So A times the identity matrix will be 8, okay? Still 8. Okay. Just like you do some real number multiplication, anything times A times 1 is still the original value, right? 8. Okay. No matrix, which means is 0. So A times, well, everything times 0, then the outcome will be 0. Okay. Okay, and the determinant, okay, 行列式啊，这是行列式，中文的行列式 determinant. When you try to calculate the determinant, then this matrix must be square. Okay, it must be square. It must be square, a square matrix, which means the number of columns equal to the number of rows. Okay, 行列都要一样，你才可以算它的行列式。Okay. Okay. This is just actually a special case algorithm to calculate 2 by 2, right? It just do the multiplication of the diagonal and subtract the other diagonal. But it's not true for 3 by 3 or anything larger than 2 by 2. Okay, it's a little bit complicated. But fortunately, you can just use science kit to determine. To find the determinant. Okay. Okay. So you can see the determinant. Okay. This is not the absolute value. Okay. It means the determinant. Okay. So A and A transpose the determinant are the same. Okay. You times times by a constant K, then the determinant will equal to K times the determinant, okay? So that's it, okay? The determinant A times B, then you take the determinant will be equal to the A's determinant times B's determinant, okay? So that's, okay? Now we talk about the rank, okay? Because it's very important when we talk about a lot of algorithms, okay? The rank will be equal to the number of nearly independent rows. Okay, linearly independent rows. So it means what? If I have something like this, the rank is what? 2, just 2. Because the first row and second row, they are linearly dependent, right? The first row times 2 will equal to the second row. So the first row and second rows, they are dependent. So the rank is only up to 2. Okay? Everyone follow? So that's how we define the rank of A. Okay? So anything. If this is no matter this is the column or row, if you can find non-zero scalar or coefficient, then you can make this equation true, then you will be linearly dependent. Okay? So which means some of the row can be represented by another row or some other rows or other columns, and then it will determine the rank. Okay? So if they are all different, for example, in this case, the rank will be 3. The rank will be 3 because you cannot find any dependency between rows or between columns. Okay? That's the rank. Okay? So-called the rank. The rank somehow for our data application could be important. Okay, it will determine the basis. Okay, I will show you what is the purpose to know the rank. Okay, so anyway, just give an example. Okay, just exactly. Usually the rank you can take the minimum or p if there's no dependency. Okay， 就是假如说它这个 matrix 是 n by p 的话，那它的 rank 最多就是这两个里面的最小值，取最小 the small number. Okay, no matter it's for column or for row. Okay, now here comes the inverse. It's very important. We put the inverse. So A times B equal to an identity matrix, and then we say B is the inverse of A, or inversely. A is the inverse of B. Okay. Okay, the inverse. Now the inverse will exist only the determinant. Okay, it's not equal to 0. When the determinant equal to 0, then you cannot define the inverse. Okay. Now. The inverse of A times B can be written down as B inverse times A's inverse, just like the transpose. Okay, the inverse of A transpose is equal to the transpose of A inverse, and the inverse, of course, you will be the original matrix itself. Okay. Now, again, this spatial case for 2 by 2 is much easier to calculate, but it's not true for anything larger than 2 by 2. Okay. Okay, so that's a simple terminology you need to remember. Okay, for linear algebra. Okay. And I would like to show you something. Okay, this is prepare myself. Okay, because okay, good. I need to enlarge. Okay. Now, most of the case we use linear algebra to solve for the unknown variable. For this example here, okay. A1 is coefficient, right? We have equation 1 and equation 2. Usually, if you have an exact solution, okay, for the linear for these linear equations. We have two unknown, which is x and y. Then you must have 2. Okay, you must 2 equations, linear equation. If you have only one equation, but you have 2 unknown x and y, which means you have an infinite possible answer, right? It can be any combination. But if you have 2 unknown with 3 linear equation, which means what? there's no exact solution unless one of the equation is redundant, okay, with another equation. So if you want to have the exact solution, the number of equations, linear equation, must be equal to the number of variables. And to solve for this linear equation, we can go for the row system, which means we apply A1, A2 here, and B1, B2 here to form a 2 by 2 matrix. Okay, 2 by 2. And this what? Then this unknown vector will be got to be 2 by 1, right? Because it's 2 by 2. When it can do the multiplication, it got to be 2 by 1. Then 2 by 2 times 2 by 1, the result will be 2 by 1. It is the expected output C1, C2. This by row system. This is what you have learned, okay? Even since your senior high school, that's what you learn by row system. Now here, there's another approach, okay? Another approach to solve for this linear equation. You can do this. Let me finish this. Okay, so A, we put this as A, 2 by 2. This unknown is 2 by 1. The result 2 by 1. So if you can find A inverse, then this unknown X can be write down as A inverse times the expected output C. That's it. Okay. So if you can solve for this, then you will have exact solution. Now, the same problem here. How to find, given two linear equation, how to find the value of X and Y. Okay. Now, we can go for the current system. Okay, we can go for this is by row system because this is row 1, row 2. Now by current, which means we take A1, A2 as a current vector. It's a current vector. Current vector times what? We times a scale. Okay, we times some scale, which is unknown. And then we plus B1, B2, which is the coefficient of the second column, okay? The coefficient of the second column here, and with some unknown scale. And the result should be equal to the expected output, C1, C2. This is by column. What does it mean? What is the meaning for this by column? It means what? In this case, we call A1 and A2 are the bases. They are the bases, 基点, which means everything can be represented by A and B if the case is in two-dimensional space. It means what? You can define any. Let me suppose this is A. Okay, a vector A. And this is another vector B. If I have a point here, okay, I want to use A and B, okay, to represent this point. What can I do? So first, I put it here, okay, and then what? If this is B, okay, I remember I have a figure here. It's much easier for you to. Okay, if this is A, this is B. Now, I need to know how many X. Okay, how many X? The figure here is not right. Okay. X times the length, this is the length of A, should be point up to here, okay? Should be up to here. 哎，这个是错的啊。那时候请学生打没打好，要放到这里哦 ，OK? And this is the basic of A. This is the basic of B. Now I need to know how many X, how many bases A, okay, here, and how many bases of B. So I can point to the expected output C. You know what I'm saying? Now you might wonder, what if, for the same case here, what if I have a point, what if I have a point right here? It's negative. Now, it can be any point here. If I have a point here, it means what? I just point in the opposite direction, which means it's minus. It could be minus 1. So it can represent, I can simply just use these two bases to represent every possible point. Everyone follow me? In a very high dimensions, for example, if you have a 100 dimension, which cannot be visual. And if you want to just use two bases, just something like this, A and B, then if we use only two bases, originally I have a 100 dimension, okay? Which means I have an X that belongs to 100 dimension. But if I use the bases, I use just two bases. Let me make it to be X hat. Then I will reduce the dimension from 100 to only 2. And you what are the value in the first dimension and second dimension? Then it will be X and Y. You know what I'm saying? We use X and Y to represent the features for, especially for time series data. We can reduce the dimension even to 100. For example, the length of 100, I can reduce it to just 2 because if you use only two bases. That's the idea, okay? That's the idea, okay? You can reduce just, and the basis, of course, it's something, deal with the design, how to design the good basis so it can have a better representation. So that's why in the early days, when people talk about the face recognition, somehow it will do something like this. For this example, you use three bases. One represents the shape of the face, and the second will represent the eyes, and the third one is going to look like the lips. And then say I use, so this code, let me call this basis 1, okay? Basis 1, this is basis 2, and this is basis 3. Okay, if for an image, it could be originally, it could be a 100 or 500 by 500. Okay, the size 500 times 500. How many pixel point you have? 250,000. Right? 500乘500 25万. Wow, the dimension is so huge. But if I only use three bases, which means I can use A1, A2, and A3. So, which means this, for a given unknown image or unknown face, I can convert it into three bases. 3 coefficients, and I use A1, A2, and A3 as the represented feature that can use to describe this unknown face. Instead to use the original 250,000 pixels. Okay, that's the in the early days, people go for this for face recognition. Of course, nowadays everybody just go for the different, but it's a very very creative idea by using the color system to define the basis, and then everything can be represented by the basis. Of course, for this case, if we want to reconstruct the face, you may need more than 3 bases. You need a lot, right? You need a lot so that you can recover, okay, or reconstruct the image or the original time. But anyway, that's one of the ways to extract the features automatically. You don't need to care, okay? You don't need to care how to design, but instead it design a good set of bases and then use the linear combination of these bases. The corresponding coefficient can be used as the representative features. 好，这是想法。那我当然讲过，你要这个影像要重建很漂亮，一定可以。当你这个基底呢用的越多，它能够表达的就会越好。可是我们现在在很多做是为了让那个 dimension reduction， 让我们的维度降维，让我们的训练会比较容易。这是从线性代数的角度来看，啊，它走的是 current system 的方式，而不是 row system。OK， 好，那所以在我们machine learning in machine learning, most of the time we use a current system, okay, instead of the row system, okay. So that's the idea, okay. That's the idea to handle, and this show you the combination. Actually, it can be any. You can use A and B to represent any point in this two-dimensional plane, okay. Of course, X and Y could be negative. It could be negative. Does not have to be positive. Okay, so I already talked about. Okay, give you more details. Okay, almost. Give me one more minute. I need to talk about. For this case here, as I mentioned, we have 2 unknowns, but we have 3 equations. So there's no exact solution. Okay, no exact solution. 不会只有一个答案，不可能，因为2个位置，你有3个方程式，不可能都满足，都满足也怪。只要都满足，那一定有一个是跟它是重复的，好，重复的。Okay, so then how to solve this problem again? Okay. We form, this is by row system, okay, A1, the first row, A2, the second row, and A3 times X1, okay. This is 2 by 3, okay. I'm sorry, 3 by 2, okay, and this 2 by 1. The result should be 3 by 1, okay. And then to solve for the problem here, then we take this as A. Okay, X is unknown, C is expected output, but because it's not square, it's 3 by 2. It's 3 by 2. It's not 2 by 2 or 3 by 3. So therefore, there's no way you can solve for the inverse. Okay, so how to solve the problem? You have learned this, but I need to repeat it because it's very important for our later application for machine learning. Okay, because it's non-square. So usually we go for this square arrow. See that? This is the arrow or the difference for the first equation. See that? Okay, we take the square. We don't care about the negative. We'll only care about the difference. 好，所以这个呢是第一个式子。Okay, 我们让 so we need to find x1 so that we can minimize the difference for the first equation. We minimize the difference for the second equation and minimize the difference for the third equation. Okay, and fortunately, whenever we solve how to solve for the linear equation problem, actually we talk about this square arrow. 最小就是只有最小平方法。Okay, so actually this is equivalent to. Okay, the notation here is a pseudo inverse. It's pseudo inverse. 因为它不是 square， 所以它没有 inverse， 所以我们用假的 inverse. pseudo 不要粽子是不是真的？Anyway, the pseudo inverse times a 3 by 2. So see that the result will become 2 by 2. Okay, it will become 2 by 2. So you find the pseudo inverse of A, then the result, okay, then you will be 2 by 3 and 3 by 1. Okay, so A plus, it means the pseudo inverse of A, and you can find the pseudo inverse as with this equation here, which means A times A transpose, then it will become square matrix, right? Then we take the inverse, okay, then times A transpose times A, this pseudo inverse. And the pseudo inverse will ensure the unknown will return the least square L. Okay? So if you have more number of equations than the number of unknowns, we go for the pseudo inverse by this square L estimation. Okay? But the calculation does not involve any optimization, so it can be fast. Okay? If the size is not too large. And I will talk about that later on. If you do the matrix like this, maybe your memory size is too small. Especially you might have an image just like 2K by 2K. Then the matrix size, and if you take this as a matrix size, it's a 2K by 2K. Well, then you will get into trouble. Okay, then how to handle it for implementation, I will talk about that okay, later on. So that's something you need to know up to now about the linear algebra. Okay, so that's it for today. Okay, next week I will starting from PCA and ICA. Okay, so see you next week. Okay. 好，这个就让你说了啊。OK。